Did you hear my back? Oh my goodness. That fucking hurts all the time. I absolutely hate my back. I hate my life. Good morning, fellow mathematicians. Welcome back to another boyish video. Today we are going to talk a little bit about nonlinear dynamics and the Kuramoto model. I'm not going to go into too much detail what this is actually about. If you want to know stuff about this, just take some lecture notes of nonlinear dynamics and you are going to find this right here. There was an exercise out of my nonlinear dynamics class and I did it this semester. I didn't do shit up until now, but there was one exercise that really piqued my interest and I just destroyed it when we were talking about the exercise, and my professor was giving props to the papa because I was doing so well. I'm a good boy, actually. Sometimes at least, and the other 3 people sitting in the class were just like, what the fuck is he doing right there at the chalkboard? Yeah. If you have watched my series on Dirichlet kernels and stuff like this, you are well suited to follow everything I'm going to say in this video. If you weren't able to understand what the Dirichlet kernel was about, just watch it and see the math magic happen. So what is this Kuramoto model about? Let's say you have a spring, and on the spring you have a lot of masses, and then you just let those go. And if you just let the first spring go, then this first mass is going to swing, but then in the process is going to start extending this other spring, and the next mass is going to start. So that's a coupled oscillator. So you have a lot of masses coupled together. And if you start with one, then all the other ones are going to swing, just like with a chaotic pendulum, for example. And the Kuramoto model is a good thing to describe coupled oscillators right here. And the first part of this exercise is to show that this phase velocity, which can be expressed like this using the Kuramoto model, can be rewritten into this expression using this right here. R times e to the I theta is nothing but this chunk right here. Okay, that's the really easy part of the exercise. All we really have to do is to consider those 2 equations as being complex numbers. And one thing, complex numbers are exactly the same if they're real and imaginary parts are exactly the same. If and only if. Meaning, what exactly is the sine? The sine is nothing but the imaginary part of the complex exponential function. So we can rewrite this upper expression as nothing but omega plus epsilon over n times the sum running from j equals to 1 to capital N of the imaginary part of e to the I. Okay, then we have phi j minus phi k. Phi j, phi k, whatever. That sounds ridiculous. And we want to equate it to this thing right here, being nothing but omega plus epsilon times r times the imaginary part of the complex exponential function, where this right here is the argument. So we have e to the I theta minus phi k. The cool thing about this real operator, this imaginary part, is that we can actually bring scalars to the inside. So let us bring this r to the inside, and here we are going to bring the 1 over n and this whole sum to the inside. And you see, one thing about the imaginary part is also we can sum up individual imaginary parts to get one big imaginary part. So if we have a complex number, for example, 3 plus 2i, and we are going to add 4 plus I to it, what we can do, we can take the imaginary part on both and sum those together. So the individual imaginary parts are going to make up the sum of the imaginary parts in the end. So that's just something you might know if you have ever dealt with complex numbers. Meaning, what that actually means is that this right here is nothing but omega plus epsilon times the imaginary part of 1 over n times the sum running from j equals to 1 to capital N. Also, we can break this up into e to the I times phi j times e to the negative I phi k, being equal to omega plus epsilon, bringing the r to the inside. Imaginary part of r times e to the I, okay, capital theta right here, times e to the negative I phi k. Maybe you can already see where this is going. What would happen if we bring this, for example, to the front and we bring this to the front of this thing? Okay, then we are going to have the imaginary part of this thing right here and the imaginary part of this thing right here. So if we set those two equal, then those two complex numbers are going to be exactly the same. So this is just basically comparing coefficients of something. So yeah, with this line, maybe it's obvious to you, maybe it's not. With this line we have actually shown that we can express this phase velocity as this phase velocity using this identity right here. So that was actually the first part of the exercise. And now we are going to go for the real deal. So the next part is the actual good part. I'm not going to go into too much detail what is going to happen here exactly after we have evaluated what we had to observe. We have to make some statement about stable points and stuff like this. That's not the point of this video. I just want to go through the calculations and show you a little application of the Dirichlet kernel once again. So we're going to set our phases, phi k is equal to some other phases, this periodic one right here and this simple phase you could say, phi. We're going to start off with this case right here, and for this I would like to plug it into here at first and see what we get. R times e to the I theta would be in this case, if we let phi k being equal to just phi, nothing but 1 over n times the sum running from k equals to 1 to capital N of e to the I phi, but obviously e to the I phi is independent of k, so we can bring it to the outside. So we have e to the I phi times 1 over n times the sum running from k equals to 1 to capital N of nothing. What is nothing exactly? Well, nothing is nothing but nothing is nothing, it's nothing but k to the 0th power. So if we just drag this out, we are going to get n terms exactly. So from 1 to capital N, so this is 1 plus 1 plus 1 plus 1, but n times is nothing but capital N. Capital N times 1 over n is nothing but 1. So we are going to get e to the I phi. Okay, so this expression is nothing but e to the I phi. Why not plug this into here, kind of? And once again, sine of this argument is nothing but the imaginary part of the complex exponential function. Meaning, our phase velocity. This time not phi dot k, but phi dot, just in this case, it really doesn't quite matter, they are equal, so if you just differentiate this thing right here on both sides, then you get that phi dot k is equal to phi dot, so it really doesn't quite matter. So this right here is nothing but omega plus epsilon times r times the imaginary part of e to the, okay, we had it before, I theta, times e to the negative I phi k, but phi k is nothing but phi. Okay, we can bring this r to the inside, and you are going to notice that r times e to the I theta is nothing but e to the I phi. So this right here is omega plus epsilon times the imaginary part of, okay, e to the I phi times e to the negative I phi is e to the 0th power is 1. But 1 is just a real valued function, a real number, so the imaginary part of this thing is just 0. Meaning, this whole thing is 0, we are going to end up with omega. So our phi dot k is nothing but some constant omega. This, in nonlinear dynamics, is called a stationary point. It's constant or 0. Now we have to deal with the second one, and this one gets slightly more complicated. Now here comes the real deal. Now we have to take a look at this thing right here, this kind of periodic phase, you could say. And once again, I would like to take a look at this expression right here. Okay, so r times e to the I theta being equal to, okay, 1 over n times the sum running from 1 to capital N of e to the I times phi k. But what is phi k? This is nothing but this right here. 2 pi over capital N k minus 1. Once again, we can break this up using the little property of the exponential function. And then we can bring this factor, which is independent of k, to the outside, namely e to the negative I times 2 pi over n. So this makes e to the negative I times 2 pi over n over capital N times the sum running from k equals to 1 to capital N of e to the I 2 pi over n times k. And here is where the Dirichlet kernel comes in. And it's really powerful at this point. At first I want you guys to remember what the Dirichlet kernel actually is. I know many of you guys hate this thing because it looks so complicated, but it's not. It's really quite easy to deal with. So if we have the Dirichlet kernel of the nth degree of tau, this is nothing but, okay, we're going to get a factor of 1 over 2 times pi of a sum running from k equals to negative n to capital N, in this case, e to the I times tau times k. We have done this before. We can make a little shift of index. We can say that, for example, s is nothing but k plus capital N, meaning also that our k is nothing but s minus capital N, so that we can plug this k into here. Meaning we get 1 over 2 times pi times the sum running from, okay, if we plug negative n into here, we are just going to get, well, 0. That's good. S being equal to 0, 2. If we plug positive n into here, this is n plus n, this makes 2 capital N. E to the I times tau times s minus n. Once again, one of those factors is independent of s in this case, namely e to the negative I times tau times n. We can bring it to the outside. We're going to get e to the, let's put it that way, 1 over 2 pi e to the negative I times tau times n times the sum running from 0 to 2 times capital N e to the I times tau times s. And we have found out what this whole chunk is going to evaluate to actually. This is nothing but 1 over 2 times pi times sine of, well, capital N plus 1/2 times tau over the sine of tau over 2. Okay, why is this good right here? Why not multiply both sides by e to the negative I times tau times n, the positive part, e to the I times tau times n, so that this thing cancels out with the other one, so that we get a 1 right here. We are multiplying both sides by 2 times pi times e to the I times tau times n. We're going to get that 2 times pi times e to the I times tau times n times the Dirichlet kernel of the nth degree of tau is nothing but, okay, we're getting rid of this factor. We're going to get e to the I times tau times n times the sine of n plus 1/2 times tau over the sine of tau over 2. Why is this good? I ask you, my boys, why is this good? This thing right here is actually also equal to this chunk. Sum running from s equal to 0 to 2 times n e to the I times tau times s. Why is this good? Yeah, it's actually really good because, well, we have a similar sum right here. Just the difference is that our index runs from 1 instead of 0 to n instead of 2n right here. And our tau is nothing but 2 times pi over n. So keep this in mind. Our tau is 2 times pi over n. How can we make this sum run from 0? Well, we can just add a 1 and subtract a 1 because e to the 0th power is just 1. So why not add a 1 and subtract a 1 right again? Okay, then we get this thing in front as being nothing but, okay, we have this factor right here. It really doesn't quite matter for our purposes. Sum running from k equals to 0 now to capital N e to the I times 2 pi over n times k minus 1. But here's another problem. Our Dirichlet kernel of the nth degree is going to run to 2 times n. But we have only an n up here, so we have to get 2 times the factor. That's not too bad, actually, because, well, n is nothing but 2 times n over 2. So our sum runs to 2 times n over 2. Meaning, this thing right here is going to be nothing but the Dirichlet kernel of the n-half degree, you could say. Meaning, all we have to do is plug n over 2 into here and see what we get. So if we evaluate this thing right here, we are going to get this factor, e to the negative I 2 pi over n times. This thing right here is nothing but e to the I times tau times n, but tau is nothing but 2 pi over n. So e to the I times 2 pi over n times, what is our n now? That was the Dirichlet kernel of the nth degree. Now we have the Dirichlet kernel of the n-half degree. Also, this is going to cancel out, leaving us with e to the I pi, which is nothing but -1, Daddy Euler right here, times the sine. We had n plus 1/2, but that was for the nth degree Dirichlet kernel. Now we have the n over 2th degree Dirichlet kernel, so n over 2 plus 1/2 times tau, which is nothing but 2 pi over n, over the sine of tau over 2, tau with this being tau once again, so 2 times pi over 2 times n. This and that is going to cancel out. -1. Don't forget your -1 right there in the end. So this is our expression at the moment, and that's not too shabby actually. So if you take a look at this right here, if you distribute this 2 pi over n into everything, we are going to end up with, okay, this is going to give us e to the negative I 2 pi over n times, okay, -1 to the front, let's put it that way. Then we have this -1 right here. And all that's really left is our sine, yeah, let's put it that way, sine of, and then we are going to get 2 pi over n times n over 2 plus, okay, 1/2 times 2 pi over n over the sine of pi over n. That's a lot of stuff to do right here. Okay, 1/2 and 2 is going to cancel out, so we have this, and also we have this 2 and this 2 cancelling out, and this n and this n. Now we have the sine of pi, so this is nothing but, okay, this factor a, I'm going to call this a at the moment, I'm terribly sorry, and then we have -1 minus the sine of pi plus pi over n over the sine of pi n. Pi n. If you're watching pi m, this is for you. Sine of pi plus something else. Okay, you can just say sine is nothing but the imaginary part of e to the I times this argument. Then we can break this up and we have a factor of e to the I pi giving us -1. So this part up here is actually nothing but, so a times -1 negative. This is going to give us negative the sine of pi over n. So this is just a shifted sine wave actually over the sine of pi over n. -1 is going to be +1. Sine of something over sine of something is just 1. So this is -1 plus 1 giving us 0. Some real number times 0 is just 0. So this is going to evaluate to 0. Meaning, overall, if we identify this phase velocity, once again, as nothing but omega plus epsilon times the imaginary part of r times e to the I, capital theta, times e to the -I times blah blah blah, it doesn't quite matter. We are going to get an imaginary part of 0. 0 is a real number, meaning our imaginary part is going to be 0 completely. So this whole term is going to be 0 because we have found this out, meaning our phase velocity is going to be omega once again. Once again, a stationary solution. And that's it. There was a lot of stuff. My head is about to explode. There was so much stuff to do and I need to catch my bus or otherwise I won't get home in time. Oh my goodness, I have to go out with the dogs a little bit. If you did enjoy this video, please like and subscribe and recommend the channel if you like. Don't forget to check out those t-shirts, my new collection, stuff like this. Oh, Papa Flammy's collection, that's so exciting. Don't forget to share those videos everywhere and recommend the channel to your friends if you do enjoy the content I produce. And yeah, that was one of the crazy applications of the Dirichlet kernel and I absolutely adore it because it's so powerful. I just love having a huge toolbox of mathematical thingies that you can use all the time and then you can impress your friends by using stuff they have never seen before and you still get the solution that's desired, so that's awesome. Yes, what else is there to say? Thank you guys for watching. Up until the next video, have a nonlinear dynamics day. See ya!
Das dritte.